It's great to have you all here today. We have a fantastic speaker today. It's Dr. Jani Saunavaara. He's a Finnish medical physicist who has specialized in magnetic resonance imaging. He earned his PhD from the University of Oulu in 2009 and became a certified medical physicist the following year. Over the past 15 years, he has worked extensively with MRI in both the public and private healthcare sectors, contributing to advancements in clinical imaging and in research. Since June 2023, he has served as a chief physicist at Turku University Hospital, where he leads his medical physics team and oversees imaging technology development and quality assurance. Since January 25, he has also holds part-time professorships in medical physics at the University of Turku, combining his clinical expertise with academic teaching and research. Before we start, to the audience, please wait with your questions until the discussion. And with this, Dr. Jani Saunavaara, the stage is yours.
Thank you very much. It's really nice to be here. Maybe I'll start a little bit more from my background. As mentioned, I haven't been working on clinical side for the past 15 years, and during that same time, the science, the research has been kind of hobby of mine. I have had some PhD students to kind of guide, and then my work, especially during the 2010-2019, when I was a medical physicist responsible for MRI, I was supporting several research groups doing research in Turku University Hospital, and that gave me opportunity to really get involved in research in very different kind of topics, from head to toe, to say, from whole body imaging to prostate, brain MRI, different kind of studies. Some purely research, some very much clinically related. But since 2025, I have had this part-time position as a professor, and now I'm kind of trying to get more and more collaborations again for the scientific part as well. Today's presentation is something that I was a little bit thinking about this topic and wondering what kind of audience I will have today. And in the end, I decided to focus on quantitative MRI technologies that are already clinically available. So meaning that I know that there are very fancy new special techniques for MR spectroscopy, for diffusion MRI, but today I'm focusing on those techniques that are already available there on commercial scanners used in clinical reality, not just in university hospitals, but in other clinics as well. And hopefully I can a little bit explain to researchers who are inventing all nice new things why it takes so long time to actually get them to clinical reality. I have some examples about successful implementations as well, and then maybe some ideas about how to overcome challenges and get these quantitative MRI techniques more to clinical use. And of course, this is something that I hope we will have good discussions afterwards. A little bit about the healthcare in Finland today. We just had this kind of healthcare reform, and after that we have had 21 well-being services counties. I'm still trying to learn to use that term because most of us are still referring to ourselves as parts of university hospitals. These colors in the map are showing that we still have this kind of collaborative areas of healthcare and social welfare that are pretty much coordinated by these university hospitals. We have 5 of those, and of course that's where most of the clinical research is done. At the same time, we have very strong public sector, but private sector is getting active as well. There is plenty of collaboration between these, and it's a little bit unique system, at least compared to some other countries, because our medical professionals, they can simultaneously have contracts both to public and to private sector. So there are people who work at the university hospital during the day and then in the evening go to the private hospital, continuing doing the same things. Of course, the good thing is that the knowledge, the current knowledge is easily transferred to the private sector as well, if there is time and money to actually take in all that new information to use. And just to point out, the Turku University Hospital is here in the southwest corner of Finland. There is one important detail that I want to point out. There is a very high level of education and training for all medical professionals in Finland. So even though it may sound at some point today that we are not taking these new techniques into use, it's not because we don't have enough understanding and education. I think it's more about the demand of high efficiency that we have today. Just the amount of doctors per 1,000 inhabitants, that's below the European Union average. And there has been especially bad shortage for radiologists. Over the past 10, 15 years, this has really been shown, and it has caused a lot of problems for the university hospitals even, but especially for the smaller rural areas. In practice, this has led to highly increased personnel costs, especially when it comes to radiologists. And on the other hand, that has given them opportunity to really spend time working extra hours on the private sector and make plenty of cash out of it. Of course, this means that very few radiologists have been interested in research efforts during these past 10, 15 years. And that's something that we have really seen. So those who are still involved, they are very busy with all the research projects, while most of the others are just focusing on clinical work, both in private and public sector. And this factor has likely affected how rapidly new MRI techniques have been implemented in clinical use, even in university hospitals. That's my opinion. If you think about my own background, it's actually in NMR spectroscopy in physics department. And I just checked the website of the research group where I used to be, and I think this same team has been there already in the beginning of 2000 when I was studying there and doing my master's thesis, my PhD. I was working with xenon atom, SF6 molecule, put it into liquid crystals and kind of evaluate these kind of new techniques, how to study properties of atoms and molecules, and on the other hand, liquid crystals as well. And then at some point, I ended up constructing this kind of xenon hyperpolarizer. So when I had briefly a visit there in Kiel, I was very interested to see all the research that you were doing there. I'm not sure how familiar you are with NMR spectroscopy or MR spectroscopy used in clinical life, but this is actually the first NMR spectrum that I was ever measuring. It's from the monodeuteurated pentane molecule. So basically very, very simple molecule, and you would expect to see quite simple spectrum coming out of that. However, when you look at this, it's nothing but simple, anything but simple. So what we are seeing here is that this monodeuteurated pentane was actually put in the anisotropic liquid crystal inside of it, which made pentane molecules to orient. And suddenly you don't only see the chemical shift spin-spin couplings, but also the dipolar and quadrupolar couplings that don't get average in this kind of environment. So this is what I started with. And of course, when I moved to the real life to see MR spectroscopy images from human brain, for example, it was quite a different story. But still, I knew how much information there is to be derived from these NMR spectrum measurements. So I was really believing in this technology when I started and had high hopes how I could make research in the field and help to get more and more advanced spectroscopy techniques in the clinical reality. Well, quite soon it came to my realization that what you can actually see from high quality NMR spectrum from MR spectrum from the human brain is something like this. This is actually very, very high quality spectrum. And what you can see is this NAA creatine column peaks usually. And how radiologists, neuroradiologists do the analysis, they make this line, and if line is pointing to that direction, there is a high NAA peak, it's a good thing. If it's pointing to other direction, it's a bad thing. It sounds very simplified, but unfortunately, it's pretty much like that. I actually checked it today from a neuroradiologist, from my colleague in the University of Oulu, and unfortunately, that's pretty much what they are all doing when they do MR spectroscopy. In research, there is plenty of potential. There are nice kind of publications telling us that there are so many possibilities with technology. There are kind of sequences available in clinical scanners that should give you possibility to do this. But in real life, there are so many challenges. We have had our own research efforts trying to do brain spectroscopy, prostate spectroscopy, liver spectroscopy, used single voxel CSI techniques, even some single voxel spectrum from brown adipose tissue. We have actually got some quite promising results, at least when we make group comparisons. But when you see the spectrums, you see the variety of the spectral width and the peak width and everything like that. You get a little bit suspicious of how well would this work for individual patient if you would try to do that kind of analysis. So there are definitely challenges when you go to the clinical world, and especially considering just single patients. It comes from the physics. Yeah, it comes from the reality that you are often looking for a very, very small target. So if your voxel is not in a perfect location, you are going to measure something else than just the finding you are interested in. The post-processing algorithms, they, at least in the past, they used to be a little bit complex. You had to have separate workstations where do the analysis. In order to get really quantitative results, you would need reference phantoms. This spectral fitting, metabolite extraction, that would require some expertise, and most neuroradiologists, they didn't have time to learn how to do it. And if it's not done on a PACS workstation, you have to go to somewhere else. It's quite often that they don't feel the need to do it. They feel that they get results from just the images they are looking at. So there are definitely challenges here. When I checked this today, there are still some neuroradiologists who are actually using spectroscopy. They use it for differential diagnostics, for tumor classifications, but to be honest, there weren't that many applications that I was hearing about. So more widespread use, that would definitely require harmonized protocols, additional training for the radiologist. Sometimes it's the medical physicist who do the analysis. That's one way to actually go around this topic, and then we just provide the results to radiologists. But this is something that we need to consider, how to actually get radiologists to use these techniques. And this is not just for the NMR spectroscopy. It's pretty much all these techniques as well. It has to be very easy for radiologists to use in order to them to really utilize it. Or then they have to have some kind of assistant, medical physicist, MRI tech, who are doing at least the pre-processing for the analysis. Of course, in addition, to really ensure that we are getting high quality results, again, not just for NMR spectroscopy, but for everything else, we really need to have this kind of automated quality checked processing pipelines. Vendor independent phantoms would be nice to actually make sure that we are measuring same kind of spectrums from scanners of different vendors. So in order to do this, we really should have early collaboration between the technical developers, clinicians, and the industry when we think how to really get spectroscopy applications or whatever other quantitative MRI techniques more usable. That's something that we would really like to have. Some other examples, when we think about relaxation time mapping techniques. Again, when I came to field of MRI, it became clear to me that at that time, at least 15 years ago, T1 and T2 weighted images, that they were the primary basis of diagnosis. So thinking about the tools, how to do T1, T2 mapping, it was clear that, or logical to think that this kind of quantitative relaxation time maps, instead of just T1 weighted or T2 weighted images, that they could be the answer to something. And in fact, these techniques, they have been available there for clinical scanners more than 15 years. I remember the time when I was first time involved in a purchase of a new Siemens 3D MRI scanner, and we were kind of going through what kind of options we have for software for sequences on that scanner. And there was this kind of relaxation time mapping applications. At that time, they were especially advertised for the joint. And when you go to Siemens website, you can still see this Mapit product that they are selling. We had some MSK radiologists very interested about this, so we purchased the application, and it never ended up to any clinical protocol. We did some tests, planned some research projects where it would have been utilized, but in the end, the use of it was very, very limited. A couple of times over the years I discussed about it, they were hoping that, well, if it would make this kind of lineation of the cartilage automatically and then just show immediately the map, maybe at that point they would be happy with it. But at that time, at least, it wasn't available. Again, I think nowadays, considering all the automated processing pipelines that are available there, that actually could be quite easily done. But again, at the moment, I have experience both from the public sector, from the private sector. I don't know anyone using this in clinical setup. I actually contacted my colleague in Oulu just to check this, because I know that they have very active cartilage studies, research group who are doing research on topic like this. And still in Oulu, they haven't got this in the clinical routine. So it's clear that sometimes it doesn't even help if you have clinicians involved in the research related to this, and still it may be that these don't end up in clinical use, even if they are commercially available there. When it comes to these relaxation mapping techniques, there are still good news. Some of them have made it to the clinical use, and well, from myself, I have good experiences as well. So, for example, this liver iron overload quantifications, one of the first projects where I was involved in a hospital was related to this, and actually we ended up using T2 mapping for iron overload quantification because it seemed to be more accurate, especially with the patients who have high iron overload. T2 star mapping is quite standard nowadays when it comes to the clinical setup and when you are dealing with patients with these problems. Cardiac mapping techniques, that's something that is quite regularly used in Finland as well, in our hospital as well. But there is a funny thing in that, because in our hospital, the people who are looking at cardiac MRI images, they are not radiologists. they actually have background in PET imaging. So they are clinical physiologists who have then done some additional training to look at MRI images. And yeah, the main task is to look at PET images, to nuclear medicine images. And on that side, I think they are more used to actually have this kind of quantitative information that gives them additional value. They have used to it. They have used to have this kind of measurable values, quantitative information from the PET studies or NM studies. And that's why they have been more happy to take these mapping techniques in use as well. I discussed with my colleague in Oulu, and she told me that, okay, they have a cardiologist who is looking at the MRI images. And the same thing there as well. He is very happy to look at the T1, T2 maps that they get. So it seems that sometimes the specialists from other field, they are more willing to take these advanced techniques in use. I have to take this synthetic MRI as a special example because I had really high hopes for this. Back in 2015, when there was first commercial applications, this was promising in the sense that at that time they kind of promised huge acceleration for the scans. That has been always one of the challenges when it comes to the quantitative MRI. People are saying that it just takes too long and it's additional sequence, we can easily do without it and so on. This technique was something that it promised that, okay, instead of taking all those different weightings, you can just use this one sequence and then calculate different weightings from that data that you are collecting. The idea there was that you have this one acquisition and you actually create T1, T2, PD, P1 maps out of it. And after that, when you have all that information, there was a software that allowed you to change the TR/TE time and create this kind of synthetic MRI images out of those. Of course, this was nice tool to get images faster, but I thought that these maps, that they would be the real big thing. Especially when you already at that point, there started to be this kind of automated processing algorithms. No one was speaking about AI or anything like that yet, but it was clear that, okay, if you can get all that quantitative information and compare that to the possible findings you have there, for example, get the information from tumors, T1 relaxation time, T2 relaxation time, then combine it with diffusion, maybe perfusion measures, you suddenly have a huge amount of quantitative data that could give you very kind of accurate information about the tumor, and maybe it would be possible to define some kind of cutoff values when it's malignant, when it's benign, and so on. The same technique, just a month ago, there was an example that it has now been used in prostate cancer detection. And they are saying that this technique showed that it was even better improving diagnostic accuracy to differentiating malignant from benign lesions in the peripheral zone compared with the conventional PIRAT scoring. We have done quite a lot of prostate MRI studies, and I can assure that this would be very interesting and valuable tool. However, this is quite often the challenge here. When you are looking at these studies, single center, relatively small sample size, and the conclusion is that larger multicenter studies with grading correlations are needed for validation. So it takes time to actually get this kind of to the level where people actually start to trust on this. And unfortunately, in the case of this technique, G is selling this with the magic name, but it is actually coming from the Swedish company called Synthetic MRI. I happen to know that their share price has been falling a lot, and their website is no longer available online. So it seems that despite all of these nice results, I know that in Sweden this technique has been used for the pediatric patients in brain scans and so on. Very promising results, quite a lot of scientific evidence, but still the transition to this kind of technique has been so slow that it seems that the company that has invented it or actually tried to commercialize it, it's not doing that well. Let's see what happens to this technique if it happens so that that company is not going to continue. But this again tells the story how long time it can take to actually get this to clinical reality, even though you can promise a lot. During this time, this 10-year time span that has been, suddenly we got these new AI-assisted image recon algorithms that made our conventional PD, T1, T2 imaging much faster. So now you can probably get the same quality of images from the regular TSC sequences in 5 minutes, 6 minutes. So the speed benefit, that's no longer there, but I'm convinced that the benefit you could get out of those T1, T2 maps, it would still be there if someone would really push and get it into clinical use. Okay, some examples that I think have a little bit better success rate. Perfusion MRI, that can be considered as quantitative MRI technique, even though some of the results are probably semi-quantitative. This is something that is very common in acute stroke imaging, for example. Clinical mainstream in acute imaging centers. You get these relative cerebral blood volume, flow, mean transit time maps out of those. But again, in the real life, it may be that radiologists are not that much looking at the quantitative values of those maps. Again, when I discussed today, I heard that the most common use for those maps is that you take the kind of analysis tool, put the line in the middle to separate the left and right hemisphere, and then you draw a ROI to one part and you see the ROI in the opposite part, and then you can make comparison from those values, if they are same or not. But the actual values, they are not that much used. On the other hand, they are just relative values, so in that sense, it's not necessarily a good idea to use them too much, but it's maybe it's not quite on the level of quantitative MRI that we are thinking. But dynamic contrast enhanced MRI, again, something that is nowadays very regular. In the past, the kind of analyzing tools that you would need to do this, they tend to be rare and a little bit expensive. Now it seems that they are much better available, and you can actually make this kind of pharmacokinetic model, measure the K-trans and other parameters. Research results are showing that this really can give you plenty of information from the tumors, additional information, and then there are other suggested applications. Sometimes this is again considered semi-quantitative, but still you would get values that I think it should be possible to actually get this to the level where you can compare this to the findings you have from other patients, maybe even from other the patients scanned with other scanners. But again, that would require quite a lot of standardization. But this would be beneficial. However, even if I think about, let's say, breast MRI patients, we have one MRI scanner that we are trying to put all our breast MRI patients in. When it comes to this more advanced perfusion analysis, they are not really used that much. I think it's seen that they are not giving enough added value. So the efficiency of this kind of efficiency-driven workflow that we have for the radiologist, they don't see that it's useful to spend time on this additional analysis, and therefore the clinical use is still limited. We are actually now planning a new research project that would go at the same time as we are scanning clinical patients, and I think at this point this data will be utilized as well. But again, it takes some kind of research efforts to actually make it as a part of clinical routine. Arterial spin labeling technique. This is something that all the MRI physicists that I know, they are really interested about. It would be a purely quantitative perfusion method. Vendors are now offering 3D sequences. It would sound that this is a nice application that would come to clinical use. I think we had first ASL, at that time 2D sequence on our scanners 18 years ago. We were using it for one research project. I had some really nice examples how it worked, and then examples how it didn't. So just happened that for some patients, it just didn't show the kind of images that you would expect. And already that gave us a little bit kind of a doubt for that technique. And in real life, radiologists, they just trust to the traditional contrast edge-based method and often want to see the contrast enhancement anyway. So there is T1 image taken afterwards, and that's why arterial spin labeling technique that hasn't really get its kind of benefits. Diffusion weighted MRI. Maybe this is the quantitative MRI success story. This is quite well-known phenomena. Plenty of research put into it, and ADC map, it's easily calculated. So radiologists, they actually get those ADC maps to the PACS workstation where they are looking at. They are coming automatically on, have always come. So that's something that is really in the clinical routine. Radiologists actually look at these ADC values at some point. They know how to draw a ROI and check what is the ADC value, maybe sometimes even compare, let's say, prostate lesions. That they know that if the ADC value is really low, then it's a malignant. If it's high, it's probably benign. But what is the cutoff value there? No one knows at the moment. There are plenty of research against assessing it. But in our case, we are scanning prostate patients on at least 4 or 5 different MRI scanners from different vendors. It means that you really cannot make a kind of cutoff values for ADC because we know for sure that there is a little bit variation between these different scanners. Again, we have a research project where we are not just on our MRI scanners, but a lot of collaborators as well, trying to get at least 30 MRI scanners involved in the study, and we try to check how much variability there actually is between those scanners. We have a prostate diffusion phantom that we are trying to utilize, scan it in the different places, and it seems that there are actually differences in basic kind of sequences that vendors offer, and now we are kind of trying to find out if there are some ways to actually get the differences smaller. Can we optimize parameters, use some more advanced sequences or something like that to really make prostate MRI and the ADC values more usable on those. But yeah, the fact is that even though these ADC maps are created and radiologists check them, they don't necessarily take advantage of the ADC values as much as they could. And it can be a good idea because, as mentioned, there are challenges. Diffusion tensor imaging, again, something really interesting when I first saw the images tractography images, of course, it was very tempting, and wanted to get more involved in this. We had research projects already 15 years ago related to this. It sounded very interesting, this FA, MD. Well, MD is pretty much the same as ADC, but this information, it really felt that this could again give additional information. We had actually researchers in Finland who were very much involved in traumatic brain injury patients. There has been really large multicenter studies kind of studying how you could use the information you can get from DTI, these FA values, MD values, how you could really use them to better understand what is the level of damage that patients who have suffered traumatic brain injury have. There was actually radiologists, neurologists having collaboration, and they were studying patients with this technique, and they ended up having this kind of lawsuits in court where patients with traumatic brain injury, they wanted to utilize these results that they get from their studies when they were trying to get kind of decision from the court that, okay, they have a bad traumatic brain injury that can prevent their regular working life and so on. So that was something where these advanced techniques, quantitative MRI, I think it was taken to the field where it wasn't ready to be used on individual level. Again, I have no problem believing that this can show something important when you are doing group analysis, but individual level, not so much. I kind of learned this already on 2011 when we had this kind of study where we had just 12 patients who were diagnosed as pathological gamblers, and then we had 12 age-matched healthy volunteers. We did this TBSS analysis, and it was a really, really clear finding that, yeah, in the FA values of these groups, when you are using this TBSS technique, you can actually see a clear difference there in multiple brain regions, and it was clear with this small population. And this same phenomenon has been seen with several different kinds of addictions, childhood development issues, and so on. I don't know if this is something that is causing them to become addicts, or is it coming from the years of addictive behavior? Can it have effect on brain? But when there are factors like this, and then you think about using this information for the diagnostic decision making for patients in traumatic brain injury, for example, there can be so many different factors that have affected on the base level of FA or MD values that you really can't use it unless you have this kind of baseline image from this particular patient. If you have scanned him or her in the age of 25 and you have very high quality DTI dataset and calculate FA maps from that, and then he or she suffers an traumatic brain injury, and you make comparison to that earlier scan, then of course you can really do it. But just compare it to some kind of standard values, I don't think that it's possible. But then, after all these negative examples, let's have a success story. 2016, we actually got this MRI-guided high-intensity focused ultrasound system to our hospital. Basically, this is an MRI scanner with a special patient table in which you have this kind of ultrasound transducer that can cause this kind of focused ultrasound beam, which again causes tissue to heat. So during the treatment, patient is lying on the table, we are getting MRI scan, seeing the uterine fibroid, and then we start the treatment. And this is the first success story. What we are seeing there, what we are observing, is MRI-guided thermometry. We are using MRI sequence that is showing us the temperature change within the patient, and especially, of course, in this treated area. And we can see when the temperature in the treated area achieves 56 degrees of Celsius, and we know that at that point, the tissue has been destroyed from that. This transducer plate in the table, it has some mobility in different directions. So even if you have a kind of a uterine fibroid of this size, patient doesn't have to move. You just change the treatment cell, and one by one, you can heat the whole region so that you can, well, in practice, burn out the uterine fibroid cells from there. The second success story in a way is this perfusion MRI that we use to evaluate how well the patient was treated. So we can make this kind of analysis out of this and check what is the treatment result. However, when we started doing this, the nice thing was that there was no clear protocol how to start, how to go with. We knew from the literature that the typical way to classify patients who are treatable, who are not, is to make this kind of Funagi classification. Again, just based on T2 weighted images. If you have this kind of very hypointense myoma or uterine fibroid, it's probably very easy to treat. There is not that much blood flow inside of it, so it will have a good response to this heating, and the treatment result is expected to be very good. When you go to Funagi 3 class, much more flow, probably free water and so on, very difficult to treat. That's usually the class of patients that we try to kind of forget completely, because for them it's just a little bit painful treatment, and the treatment results are not that good. So T2 weighted images that are the basis of the kind of this classification. To us, it immediately made sense, kind of a sense that we need T2 maps. We need quantitative values from T2 maps, and then we start making really good decisions about which patients are those that we want to treat and which are not. We did a study, and we found out that this T2 relaxation-based technique, it outperforms the Funagi classification. We decided that we could check if diffusion coefficient, ADC values, if they could outperform the Funagi classification. And it seems that they are doing it. Especially when combined with the T2 relaxation maps, we have plenty of numerical values that we can put to the analysis. It's not just the images, we then can consider other kind of patient-related information that we can obtain and combine those to the Excel charts or whatever and get even better results. Well, we kind of started to understand at some point that it's really the perfusion part that is having the most impact. So we did some advanced diffusion modeling, did this kind of IVIM study. And again, it seems that this could be very useful to not only to evaluate patients before, but we could also use this in the middle of treatment and check if the treatment is working or not. Because with the perfusion, when you are giving the contrast enhanced, doing the DCE scan, you can only do it in the end of the treatment to see the result. But this technique, you could actually check in the middle of the treatment if the perfusion is going down in the treated areas and if the treatment is efficient. This is actually something that was nice to see when you are really creating a new protocol. We heard from some Polish research group that they had seen that if you give oxytocin to these people who are getting treatment, the treatment results are getting better. They didn't actually know what's going on there, but they had an idea that it might be because of the perfusion in the uterine fibroids is going down. Well, let's take the quantitative MRI technique. Let's make perfusion MRI analysis, and we were able to find out that that's exactly what the oxytocin is doing. And quite soon, I think after 30 patients or so, we kind of transformed our treatment protocol so that all the patients treated are now getting the oxytocin. It's a hormone that it's harmless in a way, but it seems to have very good effect in increasing the treatment quality. So again, thanks to perfusion MRI, we were able to convince ourselves that this is what we are doing. Now we are having profound TULSA-PRO system for prostate. This is not actually HIFU treatment, but ultrasound treatments, and then this X-plate neuro-HIFU system for neuro treatments. And of course, we are trying to do the same thing there, utilize quantitative MRI techniques to help evaluate what patients should we treat, and especially to kind of evaluate the treatment results afterwards. This work that we have been doing with focused ultrasound, I'm happy to say that it was recognized, and we were just chosen, the Turku University Hospital was just chosen in the Centers of Excellence program of this Focused Ultrasound Foundation. And of course, it's a big motivation for us to continue our research work as well. Most of the people involved are actually clinical people who have this hobby of doing science. So in that sense, it's nice to get this recognition. So I have shown plenty of challenges, and now it's time to a little bit consider how to get over this and really get these techniques to clinical use. There are these technical and physical factors. Some of them are just there. There is not something we can do to them. There can be this kind of instability over time on the scanners. The imaging physics, of course, that's there. That cannot be changed. There are, for sure, in the future as well, sensitivity to hardware between different vendors and so on. Diffusion MRI, it will be always dependent from temperature. I don't think the susceptibility effects, they are not going to disappear. I'm pretty sure no one, at least in near future, can invent an MRI sequence that would take out the issues of P1 inhomogeneities or anything like that. Patients will be breathing, there will be blood flow, so motion artifacts, it's hard to get around. Again, long or multi-contrast acquisition challenging. That's a long task. It's a busy clinical schedule, so that doesn't really help. Well, that last part, that actually could help. If we can get those AI-assisted reconstruction algorithms to work with our dynamic, this kind of quantitative MRI sequences, this could actually change, and we could get them to the level in speed that they are usable again. This is important thing. We have to get standardization and reproducibility ensured. We have to be able to trust these quantitative numbers, even if they are scanned in different locations with different scanners or in different institutes. There is solutions for this. I'm not sure how many of you are familiar with this QIBA, Quantitative Imaging Biomarkers Alliance. It's in RSNA controlled body in the USA, but a lot of international collaboration. And they have this nice process that they really want to take these biomarkers to the industrial level, so into the clinical use. And ADC is one of those which they actually already think that it's on the stage 3, so clinically feasible technique. On the same way as there are PET-CT, FDG, SUV values, which are, I know for sure from PET Research Center, that they are not used in clinical setups and so on. So they are considering that already to be on the same level. But to get to the next stage, you have to have this kind of design method to assess site performance, then recruit sites to follow profile, and it's kind of this kind of instructions, analyze site performance data, and then go forward and forward. This is something that I think we should aim for, not only for ADC, but for other quantitative MRI techniques as well. I'm happy to see that there is now European Imaging Biomarkers Alliance. It seems to have similar goals than the GIBA has, and the nice thing to see is that they have actually already recognized this importance of collaboration. Collaboration with GIBA, but also with those people who are actually using the information that we could get from this quantitative MRI, like European Organization for Research and Treatment of Cancer. If we can get more information about those tumors, I'm sure that this organization can give better and better recommendations on how to treat those cancers. We need clinical relevance and evidence. If we get nice numbers, but clinicians don't see any use for those numbers, we are never going to get this quantitative information usable. So we need to have kind of real use for those quantitative values. And I think for that, this collaboration with organizations who kind of study those diseases and so on, it is very important. And we need to get quantitative MRI workflow very kind of straightforward, so that it doesn't take too many steps to actually get the results you need. And I really think that today, when we think about all the advances they have been with AI and so on, this shouldn't be a big issue. And when I consider, for example, that success story that I had about our uterine fibroid treatments, we are now kind of taking all that data that we have collected from quantitative MRI techniques, combine it with the clinical data. We have made Excels out of clinical data of all these patients, and now we are using AI to evaluate what are the parameters that have been indicating already before the treatment that, okay, these patients are going to benefit most, and then, of course, vice versa, which are the patients that we probably shouldn't have treated in the first place. And when we recognize all these parameters, their combined effects, we can choose patients in the future more carefully, those that are really benefiting from the treatment. Of course, there is also this kind of regulatory data infrastructure aspects. There are European Union regulations that have been surprisingly difficult to go around. I'm really hoping that it's not going to be a story with this, and at least in Finland, I think we are going to better direction when it comes to the usability of our data. So I'm hoping that this is not going to be an aspect. But there will be, I think there will be a bright future for quantitative MRI if we are able to overcome the challenges related to standardization and reproducibility. If we can get these new, faster AI-assisted recon algorithms combined with our quantitative MRI techniques, so that we don't waste time for these additional sequences. When we start getting them in the clinical routine, I'm sure that radiologists, clinicians, they start to understand their value. And of course, we can fully utilize this AI in processing pipelines as well. And not just in kind of interpreting images and maybe collecting the quantitative values, but this idea of combining it with all the other data that we have from patients, I think that will really change the game. So thank you for your attention. I really like to thank Mikko Nyman, our Chief of Radiology, for his opinions and insights, and Sem with Evelina Lammenthaus, the medical physicist in Oulu, who shared their experiences. And then Teija Sainio, she used to be my PhD student, did most of the work in those MR-hyper-related studies, and now she's working as a responsible MRI physicist in our university hospital. And of course, the rest of the HIFU team as well, they have been doing a tremendous work. So yeah, thank you for your attention, and there is my email if someone would like to get more info from these, or perhaps propose collaborations or anything.
Yeah, thanks a lot for this very interesting and comprehensive talk. So are there any questions?
Maybe I can start. Thank you so much, Jani. It's a great overview. I think my first ISMM talk was on, will spectroscopy miss the boat again? So that was a long time ago. Where do you see modern spectroscopy heading amongst those methods? Are there some techniques that you see likely to succeed, providing great benefit?
Yeah, one of the challenges I think for spectroscopy is that there has been advances. There are new techniques that would give us more information, but for some reason, vendors seem to think that they are very, very valuable tools, and the people are willing to pay them plenty of money for these. And this is a challenge. Even though there are these new techniques, they are not going to get clinical use. They are fancy things for researchers focusing on those topics, but some of them have been very expensive to take into use. I don't start to kind of evaluate different techniques between each other, but I think there is plenty of promise in that field. But the challenge I think is that how to actually get them to clinical use. That's a challenge, and even for the research sites, I think they can be a little bit pricey at the moment.
Can you name a few examples just without comparing them?
Sorry, I have been kind of not following that intensively the field, but this sorry, I don't recall the name. I have a specific technique in my mind, but don't recall the shortening for it.
Yeah, I mean, I agree with you as well that in the end it's not convincing the physicists, but there has to be an added value for the clinical workflow. And that is just very difficult to show and to convince.
Yeah, I think was it semi-laser, something like that?
Yeah.
That seems to be, yeah.
But I keep my questions to myself first. The stage is open for anyone else.
Maybe I would like to ask from you if this, what I was telling about the situation in Finland, is this something that you feel that is the same? Is it same in Germany? I suppose you are most from the university hospitals, so do you think that these techniques are more used in clinical routines in your sites?
Do we have a clinician in the audience who can answer that better than my attempt? So I think in the private offices, and now I'm speculating, right? In the private offices, I don't think much has arrived. Yeah. There as well, time is money, right? And short sequences are run, and I mean, time is money. It's everywhere. I think it really depends on the focus areas of the hospitals where you are. If there is like an ASL focus, ASL may be run because some senior people would like to have it added. Yeah. Otherwise not.
Yeah, that sounds very familiar. I heard that in Kuopio they are doing more spectroscopy than in other places, and then I found out that the neuroradiologist, who is the head of whole department, has a very strong background in spectroscopy research.
Yeah.
So it makes sense. He knows what it can do, and he has courage to utilize it in clinical reality, but probably takes time before it actually starts to kind of get in the wider use in Finland.
I think a larger milestone is made if it makes it into the guidelines, right? If it's a recommendation, a consensus recommendation.
Yeah.
That is difficult to achieve.
Yeah, if I think about how the prostate MRI, for example, has gone, and they started to have these strong recommendations of what kind of protocols to use. And I think some of our researchers were one of the first to suggest that, yeah, the T2-weighted and diffusion-weighted images only, that could be enough. So not necessarily even need to use the perfusion if you are doing this kind of some kind of screening, not necessarily doing specific analysis, so that you would know that there is a patient with prostate cancer, what kind of getting evaluation if there is something or not. And that actually was getting quite a lot of opponents at the whole idea about doing it like this. And I think now at some point there was a recommendation that yeah, this is enough if you are just doing screening, because when you kind of forget the DCE, the spectroscopy from the protocol, you can actually make it in 15 minutes, 20 minutes, which means that you can get much more patients through the MRI. And in the end, in the big picture, that will help to identify those patients who really need the treatment.
Yeah, for sure. I agree. And so again, right? Please, anyone, raise your arms, and we will take questions. But I will keep talking until you do.
I can't find the raise arm button. Oh, sorry.
All right. Yes, Vitaly, please.
Yes, sorry, I didn't want to interrupt, but I really can't find the button. Great talk. Thank you for this nice overview. I found particularly interesting that you mentioned DCE MRI in your list of semi-quantitative methods.
Yeah.
I have two questions regarding that. Is there like standard model used in, let's say, or accepted in clinical practice for all these pharmacokinetic modeling? So if there is one, can you name it? And the other one is maybe you can comment also on the fact that all these parameters are actually derived from T1 weighted images and not from T1 parametric maps.
Yeah.
So how does it make it interpretable and comparable?
Yeah, to be honest, I think there is no consensus. If you think about these K-trans and parameters like that you can get, at the moment they are somehow believed that these are giving you added value and so on, but I don't think that they can be said that those are clinical standard, at least not at this point. But when you get a tool from a vendor for your analysis workstation or server that is CE marked, as some of these are, then I think it should be considered that it's reliable enough, at least. I was thinking if the TOFTS model, I think that's at least used in one of the applications that I have run into.
Do you have a feeling where DCE MRI goes in the routine application with regards to the use of gadolinium?
Sorry, where?
I'm sorry. First, Vitaly, does that answer your question, or do you want to ask more?
No, that's a great answer. Thanks.
I was wondering, where do you see DCE MRI going with respect to the use of gadolinium?
MRI, do you mean that could we reduce the number of the amount of gadolinium that we use in the studies, or?
Yeah, I mean that it adds another burden on the use of the technique if you know that you should not use much gadolinium anymore.
Yeah.
Is the added benefit then outweighing the risks that you put by injecting the gadolinium?
Yeah, I think for the most cases where we use the gado and take the dynamic contrast enhanced images, the radiologist would still like to see the contrast enhancement anyway. So this DCE MRI is kind of additional sequence that is just scanned at the same time as contrast agent is injected. But even if we wouldn't measure it, the radiologist would still want to see the contrast enhanced images. So in that sense, I don't think that it would change the use of gadolinium.
Yeah, I see. Okay, so if it's anyways acquired, anyways needed,
yeah,
the gadolinium.
Yeah, but I think it's giving added value, but the added value is not often utilized. So that's a challenge in my mind.
Thomas Kampf has, hi Thomas. Thomas Kampf has a comment. Although not DCE, but DSC is quite the standard in brain perfusion imaging with MRI. Because the effect is higher and the measurement time smaller, and nearly half of all patients get contrast agent anyways.
Yeah.
Okay.
Yeah, it's as I mentioned, it's really important in these acute stroke cases, for example, that really defines the treatment. When we got the new kind of emergency department, we wanted to get MRI scanner that is only serving patients on the basis of how they come in. So there are no fixed timetables for that scanner. And it was especially important for these acute stroke patients. We get call already from the ambulance that now there is a patient coming. We make clear for the room if there is another patient inside the scanner at that point, we may intervene and take him or her out so that the stroke patient can come in. We take the perfusion MRI, fast diffusion, radiologist makes the decision, and at that point, the kind of treatment line is chosen. If there is a short time from the actual incident, then there is a different treatment than in the case there is 6 hours from the incident. That you can evaluate from the perfusion and diffusion image, the time that has actually been from the incident, and that will have enormous impact on the treatment that is chosen. So that's why it's so important in clinical reality.
All right, last chance for anyone.
I think Kolja has.
Yeah, so I was pretty impressed from the 1H NMR spectrum of the monodeutylated benzene, and then I was just wondering, does these quadrupolar and dipolar couplings shows up in any MRS application, or can they usually be neglected?
Yeah, I think they can be safely neglected because you really need to get molecules oriented in all the same way so that you can actually see these interactions. So this is very specific method how to actually observe those dipolar and quadrupolar couplings, and it was kind of specialty of that research group where I started. So
okay, so there's not even a single application.
Yeah, to be honest, I don't think I have ever seen a spectra like this from any other research group. So
okay,
that's very specific team for them. But yeah, it was nice experience to see what you can actually get when you really get all these interactions visible.
Yeah, that's true.
Yeah, and of course, what they are actually doing, those are quite small molecules, so they can model the interactions and kind of get more information from the comparing their models to the these experimental results that we got, and I think that has given a lot of understanding about the underlying physics of those interactions.
Do you remember at which field strength this spectrum was recorded?
I would say that this was 500 megahertz spectrometer, so meaning that it's 11.7 Tesla.
Okay, thanks a lot.
All right. If there's no more hands raised, questions asked, then we would like to thank you again for being with us tonight. It was fantastic. Great talk, Jani. It was a pleasure of hosting you, and we hope to see you again sometime soon.
Yep, thank you. And if you get ideas about possible collaborations, don't hesitate to contact me.
Yes, we have a first draft, right, or a first thingy we have.
Yeah. I'm actually still making some modifications, but I was able to get some collaborators involved from the Finland, and let's see if we could get some collaboration in the fields of DTI Alps.
Yeah, it's very good. Thank you, Jani, and thanks everyone else for joining us tonight. Have a great pre-Christmas time and good vacations.
Same to you all.
Okay. Bye-bye. Yeah, Jani, thank you so much. It was very cool.
Yeah. I was wondering about that spectroscopy technique, but I think it was simulation. I have a PhD student working on the topic still. He has been mentioning that this could be something that he would like to utilize. But I know for sure that there are some other kind of really promising techniques as well. The only challenge is that he doesn't have enough time. He's already in clinical work as well, and that seems to be the big problem when you want some research to actually start up from nothing.
Yeah, I would just be interested in seeing if there's really an added benefit, right? And of course, there can be a lot of added benefit for research, but you need to do it once or twice or so. Yeah. But it's a difference then you have your treatment affected by it. And of course, with brain tumors, there are just limited treatment options, for example. Yeah. The treatment outcome is just not very good, no matter what you do.
Yeah, but when I think about the history and what we tried to do to actually improve those spectral quality, we were doing interpolation and so on. If you think about what some of these AI recon algorithms are now doing, they are doing advanced kind of interpolation, noise reduction, and I can't help thinking if we could actually try to do that same thing with these NMR spectroscopy experiments.
Yeah. The question is a little bit like, do we see smaller changes or do we see other metabolites? What I find interesting, but I have not looked at into too much detail, is the this J-resolved spectroscopy, where you basically don't have much spatial resolution, but you get like 20 metabolites in the brain. But at the cost of no much spatial resolution.
Yeah.
But I have to look into that more closely.
Yeah, I remember the chemistry department guys who were working there with this kind of structure. They didn't know the structure of the molecule, so they did this kind of very advanced NMR spectroscopy studies to try to figure out which kind of atoms there are, what is the molecular structure, and so on. And those techniques that they had, those might actually give some kind of added value to us as well. But I think usually it's quite heavy RF pulse setup that you are using to get it. So I can't help thinking that there might be issues with SAR, for example. because I remember that there was actually this one experiment. They blew up the spectral tube in the animals because they were irradiating it so heavily, trying to get the proton signal kind of or proton interactions out with carbon or something like that. They just forgot to kind of think about how much power they are actually putting in it. And very long experiments. So the sample was heating, and it was this kind of sealed sample, so it ended up exploding. So
it's actually possible with MR.
yeah, it is. When you have NMR machine that doesn't control your SAR, anything can happen. So. And of course, very high frequencies when you have this 600 megahertz.
Yeah, sure. Yes, absolutely. Yes. And small coils, high RF amplifiers.
Yes.
Yeah. Thank you again for your time this evening. And yes, we're in touch anyways.
Yes, it was really nice to have this opportunity. Bye.
See you, Jani.